This is the story of the one. As head of maintenance at a concert hall, he knows the show must always go on. That's why he works behind the scenes, ensuring every light is working, the HVAC is humming, and his facility shines. With Grainger's supplies and solutions for every challenge he faces, plus 24/7 customer support, his venue never misses a beat. Call quickgrainger.com or just stop by. Grainger, for the ones who get it done.
When it comes to weight loss, no two people are the same. That's why Noom builds personalized plans based on your unique psychology and biology. Take Brittany. After years of unsustainable diets, Noom helped her lose 20 pounds and keep it off.
I was definitely in a yo-yo cycle for years of just losing weight, gaining weight, and it was exhausting.
And Stephanie. She's a former D1 athlete who knew she couldn't out-train her diet, and she lost 38 pounds.
My relationship to food before Noom was never consistent.
And Evan, he can't stand salads, but he still lost 50 pounds with Noom.
I never really was a salad guy. That's just not who I am. Even through the pickiness, Noom taught me that building better habits builds a healthier lifestyle. I'm not doing this to get to a number. I'm doing this to feel better.
Get your personalized plan today at Noom.com. Real Noom users compensated to provide their story. In 4 weeks, the typical Noom user can expect to lose 1 to 2 pounds per week. Individual results may vary.
Attention truth seekers and probability enthusiasts. The time has come to unlock the secrets of the universe. In this episode, we'll embark on a mind-bending exploration of Bayes' theorem and its astonishing implication and the potential to predict everything. Yes, you've heard that right. Everything. From the weather on Mars to the winner of the next year's lottery. Bayes' theorem offers a powerful tool for making informed guesses about the future. Now, hold back your hats. Bayes' theorem isn't something mystical like a crystal ball. It's a mathematical framework that allows us to update our beliefs based on the new evidence. Let's say you hear a strange scratching sound coming from the attic. That's a prior probability. You might believe that it's a harmless squirrel. That makes sense, right? But then you see a shadowy figure just dart across the window. Oh, wait, that's some new evidence. And suddenly your belief is that it's a sneaky raccoon that skyrockets. You know, just your basic posterior probability. See, with every new piece of information, Bayes' theorem helps us refine our predictions. The more data we gather, the closer we get to a clear picture of what's happening or what might happen, right? So, imagine a world where weather patterns are no longer a mystery and where market trends can be accurately forecasted, where even the next technological breakthrough can be predicted in a high degree of certainty. Bayes' theorem, my friends, holds the keys to unlocking this level of understanding. But it's foolproof. Can we truly predict everything? That's a question that we're going to grapple throughout the show. So join me, Autumn Phaneuf, your host at Breaking Math Podcast, in this episode to chat with Tom Chivers, an author and award-winning science writer for Semaphore. His writing has appeared in The Times London, The Guardian, New Scientist, Wired, CNN, and so many more. His books include The Rationalist Guide to the Galaxy, How to Read Numbers, and last but not least, Everything is Predictable: How Bayesian Statistics Explain Our World. Its release date was this past weekend in the U.S., May 7th, at most large retailers. So let's dive in. So we're launching the podcast a couple days after, but we are super excited to have you on the show, Tom. How are you doing this morning?
I'm very well, thank you. Yes, yeah, it's fun to talk about the Bayes stuff. I'm still having to remember a lot of the stuff because I wrote the book a long time ago, but it's a year ago now. But it's still it's exciting, and hopefully you'll enjoy it as much as I do.
Yes, actually, I read the whole book.
Oh wow!
Yeah, cover to cover, and I have been actually jazzed about interviewing you for this because my background is industrial engineering and mathematics. And, you know, you talk about the things that Mathematicians, you think everybody goes from one thing to the next, and that stuff is boring.
Mm-hmm.
Right? Math is
Yeah.
boring. It's not. We
It's
have a lot of
not.
quirks.
There's a lot of interesting things about it. There's a lot of there's a lot of ways to interact with like decision making and how we live our lives. And actually, you can use some quite simple maths. I mean, that's the thing I like about Bayes' theorem, is that it's really simple in its sort of conceptual stuff. I mean, it's all like it's multiplication and division. You know, my 8-year-old daughter could do all the basics that you require for it, but it has these really profound implications for so many areas of the world. I will say I'm absolutely thrilled that you've read the whole book. Like, I think you're the first person I've met who's done that, who doesn't literally work on it. So that's very cool.
So yes, I love reading a lot of different math books and just science in general. And I'm curious, how did you get involved in science journalism and writing?
Right. Okay. So, I mean, well, obviously, like any good science journalist, I have a degree in philosophy. So I don't know. Yeah. So I started out when I was young, I was just always just interested in stuff. I was always like an intellectual like magpie. I wanted to learn about as many different things as I could. And the way that you get to do that at university is to do philosophy. So you do philosophy of whatever, philosophy of science, philosophy of mind, philosophy of language, you know. After uni, after that I did sort of I did like more study, more time at university doing a master's degree, and then started but never completing a PhD, which was in sort of ethics of science particularly. And then the PhD was in the ethics of science journalism. Didn't have a clue what I was doing. Completely made up nonsense. Had never worked a day as a journalist in my life, so it was like being yeah, yeah, it was a bit crazy, but it was like being a I don't know, a lepidopterist who's never seen a butterfly or something. You know, it was a weird decision. But anyway, after that, I had to go and get a proper job. Fell by sheer fluke into a job at a national newspaper, and then and sort of steered my way towards sciencey things from there because it was what I was interested in. And how I ended up getting involved in the book, particularly, I've sort of been aware of Bayes' theorem for years. I remember reading about it in this British journalist and sort of medical doctor called Ben Goldacre's columns in the early 2000s, and it was just, you know, I remember finding it. What do you mean a test can be 99% accurate, but there's not a 99% chance that it's right? I don't understand what you mean, and I just found it fascinating. But then, and so both of my previous books, it's played a pretty central role in them because I just find it so interesting, and it seems so crucial to sort of our understanding of so much. But what particularly drove me to write this book was that in my last book had a chapter on Bayes. I wrote an article about it for a British newspaper, The Observer, and the editor put in as just an after, you know, not as a big deal. He described it as like how this obscure theorem just describes the world or something like that, you know, in what I think the Americans call the deck, you know, the headline, the bit below the headline that isn't the main. Anyway, he put it there, you know. It drove people mad, absolutely mad. I had like 4 days of people raging in my Twitter mentions, going, you know, how do you dare you call the Bayes obscure? It's central to probability theory and all this sort of stuff. Like, well, yeah, I get where they were coming from, but actually, I bet you 90% of the population has no idea what Bayes' theorem is. No idea. Like, so I felt, you know,
90% of mathematics professors and graduate students had at least one question wrong. So,
yeah.
Do they know what statistics is? You know,
yes, exactly.
Who's a fine oiled machine who's taught this? They're like, there's human error.
yeah, exactly. So anyway, I got it was after like 3 days of what I ended up describing as obscure gate, because it was like one of the biggest, it was hilarious, you know, this enormous Twitter storm, or it feels enormous when you're in the middle of it, over what, you know, this incredibly
it's
sort of
always an enormous Twitter storm.
Yeah, exactly. So after that, I was sort of driven by pure spite, really, because they were like professors of biostatistics and these sort of, and I remember a Stanford PhD, Stanford statistics PhD guy all weighing in and getting all snotty about it. And I was like, you know what? I'm going to write a goddamn book about this. I'm going to write a book and it will be about Bayes' theorem, and it will show you anyway. So I did that, and that's what you have now read. It is a product of pure spite.
It is the most brilliant spite book.
Yes, thank you. That's really kind.
As I like to say, surviving and thriving out of spite.
Yeah, no, it was a lot of fun.
We are.
Yes, exactly.
So, beyond that, like, where does the story start for Bayes' theorem? I know science and religion just don't mix. But now you have math and religion and Thomas Bayes. So I'm curious how the narrative came along. Yes.
Yeah. Well, so Bayes himself was at the sort of end of, like, he was there'd been a couple of 100 years probably of people thinking, or certainly 150 years, people thinking about probability up before Bayes, and that they'd been trying to work out things like, the classic thing is the problem with the points, okay, which was Fermat of last theorem fame, and Pascal, Blaise Pascal, another great French mathematician, working out, like, if you imagine two people playing a simple dice game or something, how do you work out, and they have to stop the game before it finishes, how do you work out what the fair way to split the pot is? So, like, if I've got 2 points and you've got 1, and it's a game of first to 3, what's the, coin tossing or whatever, what's the fair way to split the pot? And there've been centuries of working this out, like, should it be like, I've got 2 and you've got 1, therefore I should have twice as much as you, or whatever? And they had the insight that it's about how many outcomes there are from where you are, and so yes. in a 2-to-1 game, then there are 4 possible outcomes remaining, and the guy who's 2-to-1 ahead would win in 3 out of 4. So the fair thing is to split it 3 ways, 3 parts to 1. Anyway, so the probabilities sort of went down this route, and then Bernoulli was looking at things like the law of large numbers. But what all these people were doing was looking at how likely you are to see some result, like, for example, player 1 winning or player 2 winning, or number of balls drawn from some urn full of black and white balls, whatever, that sort of thing. How likely you are to see some result given a hypothesis, like, or given some state of the world, like the people are playing a game. But what statisticians and scientists really want from probability is to be able to say, how likely is it that my hypothesis is true? How, if I could do a COVID vaccine trial, say, right, how likely is it that, and I get, in the placebo arm, 10 people get COVID, and in the treatment arm, the actual vaccine arm, 1 person does. The vaccine didn't work. That would be the same. Yes. That would be the problem. But what we want to know is, how likely is it that my vaccine does work? How likely is it? What's the probability that my hypothesis is true? And it was only Bayes who. It was when Bayes did it. Bayes was the first person to come up with that way of doing it. And he realized you have to use prior probability. You have to use your subjective estimate of how likely things were before. And the religion side of thing was, well, he was a Presbyterian minister, well, not a nonconformist minister. So in England in the 18th century, there you weren't allowed. You had to follow either the Church of England's rules. I mean, this is obviously quite relevant to America, because a lot of Americans left for that exact reason, or they weren't Americans at the time. So Bayes was, he had to go. He wasn't allowed to study in English universities. Had to go to Edinburgh in Scotland. He couldn't preach in official C of E churches and all sort of stuff. But anyway, he was also as well as being a preacher, he was and I say this with enormous love, but he was a real nerd. He was a massive nerd, right? He was a hobbyist mathematician.
Anyone listening to the podcast is a massive nerd.
Yeah, of course, and I say, and I love them as well. I consider myself very much a nerd, right? That's my whole thing.
I guess anyone with at least a master's degree, if not a PhD.
Yes, yeah, exactly. It's a strong possibility.
Possibility that someone's a nerd.
Yeah, you can do a Bayesian thing there. What's your prior probability of someone being a nerd is like, probably about 5%. When you hear they've got a master's degree in something, that should go up by at least threefold. Anyway, so he was he'd got involved with this whole sort of coterie of other hobbyist mathematicians hanging around in southern England around this one Lord Stanhope guy who funded them all and let them. It was a bit like I had someone comparing to me like rich people nowadays might get involved in sports teams and stuff,
Yeah.
but back then they got involved in science. They spent their endless leisure hours writing papers for the Royal Society and that sort of stuff. Where religion also comes into it, you might like, is that after Bayes' death, his friend Richard Price, who was which I love this detail. He was a friend of Benjamin Franklin's and a friend of John Adams and I think Thomas Jefferson. Like I was, I'd have to look back in the book, but yeah, a friend of these amazing founding fathers.
Yes.
Yeah. He was another nonconformist preacher, and he was very interested in using Bayes' theorem. Here's one who published the theorem after Bayes' death in the Philosophical Transactions of the Royal Society, and he wanted to use Bayes' theorem to defend God, defend the idea of God from Hume, David Hume, the philosopher, because Hume had sort of said, like, the classic thing of extraordinary claims require extraordinary evidence. If you want to say that a miracle has happened, it needs to be more plausible that the miracle happened than that the person who's telling you about the miracle is lying to you. And so he's saying you can never really believe in biblical miracles, for instance. And Price, obviously being a preacher, being a man of God, he wanted to say, actually, it is possible for unexpected things to happen, and you can never be certain that they don't. And he used Bayes' theorem, which baked into the maths of it pretty much is the impossibility of ever finding certainty. Although that might be a bit of a paradox now I say it out loud. But he was saying that it was impossible to, no matter how many times you see the sun coming up, you can never be sure that it didn't another time. And he therefore argued that no matter how many times you see people not coming back from the dead, for instance, it doesn't mean it didn't happen in the past. So he was using it as a way of defending biblical tradition from Hume. I'm not saying he was successful at that, but that was the idea.
Okay. So with that, out of curiosity, where does this go with innovations in science and math, and how does this play into like what we're doing now?
Okay.
Right.
Well, finish the question. Sorry, I talked over you there.
So, what if there was one overarching theory that could help explain much of our modern day lives, right? So we're looking at how does this play into AI more?
Yeah.
The big topics that we about.
Yeah. So, I mean, the classic Bayes' theorem application is usually medicine, right? That's how it usually comes along. People talking about cancer screening or COVID tests, if someone says a test is 99% specific and 99% sensitive, so that is, it only returns, if you have the condition that you're testing for, it only returns a false negative one time in 100. Let's say if it's 99%, or if you don't have the condition, it will only return a false positive one time in 100. So that sounds like it should be, if you take the test, there's only a 1 in 100 chance, and it comes back positive. There's only a 1 in 100 chance that it's a false positive, right? But I was thinking about this the other day, what the best way of demonstrating it was, and I was saying, imagine that I went and took a medical test for some condition or other, and we know that it only returns false positives 1 time in 100, and I go and take the test and I get a positive result. How likely is it that I have the disease? And most people would probably say, 1 in 100. But then if I said, but what if it was a pregnancy test? And then
what if it's one new rapid COVID tests that nobody is showing positive for?
Yeah.
Or you get a box and that it shows that you're positive.
Yeah. But I mean, like if it was a guy who looks like me taking a pregnancy test, then most of us would think the chances are it's more likely that it's a false positive than that it's a true positive, even if false positives are pretty rare, because if you test 100 people, you might get the false positive once in it, and that's more likely to happen than that I am unexpectedly pregnant. Yeah, I'm quite old now, so it would be surprising. But yeah, I know it. Yeah, well, exactly. There's still hope yet. So that's the classic thing, So if you do a cancer test and you get this very accurate cancer test, but it returns positive, you can't know how likely you are to have cancer unless you know how likely it was that you had cancer in the first place. You need to compare the hypothesis, the likelihood of the hypothesis, this is a false positive, to the likelihood of the chance of the hypothesis, this is I have this very rare cancer. But what Bayes' theorem does is force you to look at how likely the two hypotheses are, and that means you have to know how likely your thing was in the first place. And so that's the classic application, but it comes into a million different varieties. I mean, you mentioned law. There's a classic thing.
Have court cases, right?
Sorry, yeah, exactly. You have the thing called the prosecutor's fallacy,
yes,
which is literally just not thinking like a Bayesian. Really, it is that you. A lot of times, a prosecutor will say in a court case, for example, there was an awful case in the UK which I really shudder to think about. But this poor woman, two of her babies died of cot death, and it was that's a very rare condition. And a doctor told the court that since the condition is only happens, I can't remember, it was 1 in 17,000 times or something like that. He said that 1 in 17,000 times 1 in 17,000 is 1 in whatever it was, some number of millions, and therefore the chance that this woman is innocent is only 1 in however many millions, and she went to prison. But as other people, as statisticians pointed out, what he's done there is the Bayesian mistake of assuming that the chance of seeing
something happen.
Yeah, the chance of seeing this result given a hypothesis is not the same as the chance that this hypothesis is true given a result, any more than saying only 1 in 8 billion humans is the Pope is the same as only a 1 in 8 billion chance that the Pope is human. They're just different. They are different questions, fundamentally different questions, and what you need to do is compare the likelihood of the probability, the likelihood that this test came back, this was a coincidence versus the likelihood of a woman being a double murderer, which is also extremely unlikely. So you need to compare hypotheses. So it absolutely comes into the law. With AI, it's fascinating in a way because all AIs are really doing is
statistical probability,
predicting stuff. Yeah, exactly. It is predicting stuff. So whether it's when we say that ChatGPT, we ask ChatGPT to say, we ask we ask it, how are you, and it says I'm very well, thank you. It's not doing that because it is very well. It's just predicting that that's the sort of thing a human would expect to hear or would say given that string, that prompt, right? And obviously, what Bayes is the maths of prediction. But when we make your prior is a prediction, and you update your prediction with new information, new evidence, and and
when you're doing something like a LLM with AI, you have your basic language. You have the language learning model there that just takes it from what you're doing, and it automatically will predict the next few words.
Yes,
and it just makes things much more, easier for people to just think about and just hit the tab button when they're just writing something, or you just go to that next thing, right? And you can go to your next stuff.
For the ones who know safety isn't a catchphrase, it's a culture. And the ones who help make sure everyone makes it home safe. For the safety-minded who watch everyone's backs, Grainger offers supplies and solutions for every industry, as well as safety assessments and training to keep your facilities safe and your people safer. Call, click Grainger.com, or just stop by. Grainger, for the ones who get it done.
Automatically. But what is the danger of that when we're thinking about that with ethics, right? So...
that's a bigger question, isn't it? I mean, what I will say about LLMs that I find difficult. There's a lot of people saying that it's just predicting what we'll say next. Now, I always find people put the word "just" before things, and I always think that he's just flying by flapping his arms. He's just running 100 meters in 9.6 seconds. It's very easy to say "just," but actually predicting things is very difficult, and that's why humans are good at surviving in the world, because we predict what the world will be like, which a stone can't do that, right? So AIs, there's evidence they do build models, but yes, the world is slightly off the topic of the book, maybe, but it's definitely going to be the world's going to have a complicated time working out the ethics of how AI, as AIs predict what humans would do to create art, for instance, and suddenly we've got machines that can create beautiful art for us, which isn't human made. How do we deal with that? Is it copyright? That's all. That's going to be very complicated, and I don't know how. Luckily, I don't have to answer those questions.
So it's been popping up in a lot of trading card games.
Really?
Yes. So a lot of the artists that are in the I'll say smaller art market.
Yeah.
There's been posters that have been put out by. So there have been trading card games in which we have seen the art. And usually the people that play it that are very competitive, I know that I'm a competitive trading card game player. And on many occasions, you look at the cards, you look at the art, and you say, was this done by the artist? Was this done by a certain person? Was this faked? Right? And you know that there's certain features in the art, even if it is AI generated. Where do you look at these things? You look at the fine details. You look at the border for somebody's shirt, right?
Yeah.
You look at the tiny patterns in there. And the predictability, I will say, and cohesiveness of something, if you're looking at a big picture, it looks fabulous. You zoom in on something that's smaller, fine detail, you'll realize that instead of a square, it goes square on one side of your shirt, and then it'll be a circle on the other, for like the lace or the border. Yeah. And then if you were looking at something like body armor, right? It will have like a triple border somewhere, and you'll think of like on your shoulder pads. Then you look at a chest piece, and it only has a single border or a double border, and things are not cohesive in that sense.
Okay, so they're not doing a brilliant job. Well, I will say, like, they're not. That's exactly. Look how fine you have to look at. Imagine 5 years ago an AI doing that, and it wouldn't get anywhere near. The progress they made has been astonishing.
Absolutely, and it's just that. It's all those fine details for the AI. I don't know if it will ever line up to the human expectation. Even as someone, so think of it a bubble, right?
Yeah.
You cannot get every single pattern predictably correct. I would say...
No. Okay, sorry, carry on.
I would say AI and machine learning are a great aid to getting the result that we need. However, when you're looking at the very fine details of, say, a mathematical proof that we haven't solved yet.
Yeah.
If we're looking at some sort of new discovery, we can only look at these things based on the facts that we already have. And just knowing that the majority of things, I will say for AI, it will be correct within 2 standard deviations.
I think that's probably. I certainly think that's true now. I've been, because I wrote my first book was about AI,
right?
And that came out in 2019. So 5, and I was writing it in
about 5 years ago.
Yeah, about 5 years ago, which is ridiculous. Okay, that's obviously can't be right. 2019 is not 5 years ago, but somehow it is.
No, it's never.
Can't be. Yeah. Anyway, so and I remember when I was writing that, it was still pretty big news that an AI image classifier could reliably tell the difference between a cat and a dog. And now we are well past that, And back then it was there was, but not long before then, 3 or 4 years before then, there was that famous XKCD comic about someone saying can you write me some script that can tell me where this photo was whether this photo was taken in a national park? Easy, I can do that in a second. And then tell me whether there's a photo of a bird. And then, nope, that's going to take me 5 years. 5 years and a massive research team. It's just the progress has been astounding. And I agree there's a strong, the edge cases constantly get harder. And you see this with self-driving cars. It'll get ironing out the last little wrinkles gets harder and harder, getting closer and closer to perfection. You get law of diminishing returns. That said, I am very wary of betting against them not doing it to a significant degree, because I do think you just look at how much better it's got in the last few years, and I agree. At the moment, you can always detect little things, or often detect little things that aren't quite right, but it happens less and less with each thing that comes out.
Yes. The hardest things in art to do are, this comes as more of a blanket statement. So I usually combine, my background is partially in art, partially in math. So I do a lot of like origami and mathematics, and of that sort. But when you're looking at art, even as an artist, even as an illustrator doing computer generated stuff, the big thing that we look at is the fine details of hands, hand posture. And it has proven relatively true that being able to create any sort of toes, hands, I'll say phalanges in general, is one of the most difficult, fine-tuned things for AI and an artist to be able to do.
Yeah, I mean, that's obviously, it was only about a year ago they just couldn't do it. You could always look and know I've got 6 fingers,
Yes, at the moment, so say May of 2024, it's still of that sort of issue. Yeah,
but I mean, then I will, my 2 comebacks to that, not that I'm disagreeing with you exactly, but again, I think the hands problem is less dramatic from looking at like the output from things like Midjourney now. It's less dramatic than it was. They reliably have 5 fingers most of the time now. Sometimes they then have 2 left hands or something. It's by no means.
We know that it was a right hand.
Yeah, exactly. But I mean, I will also say that hands are like, it's not as if humans get hands right. Like, you look at the bits that humans draw and get it wrong. Even like the front, I know, I can't remember who it was exactly, but there was some comic book artist who you noticed always seemed to have hands hidden behind stuff and things because they were such a pain. Like, even like professional artists struggle with hands. So I want to give the AIs a bit of a pass on some of this stuff.
Yep, absolutely. Now, out of curiosity, where are these major predictions that we have, whether it has been in AI or whether it's in a court of law, politics, voting, where are these things going wrong?
Well, I mean, one way in which predictions... So like an obvious way in which predictions go wrong is in conspiracy theories, right? I think this is a thing that we might not think of as being a Bayesian phenomenon, but it kind of is, because like what Bayes tells us is that how our predictions of the world, and therefore how we interpret incoming evidence, is very much based on what we already believed. That's our priors and that we update our prior probabilities with new evidence to come with our posterior probabilities. And there's a sort of with conspiracy theories in particular, I think what I should stress first is that like all human activity is to some extent predicting stuff. When we are each breath we take, when we're making any sort of decision, we're predicting that this decision will be better than the other decision, that will have these outcomes that but when we have beliefs about the world, they are sort of predictions about how the world will behave. So very crucially, a lot of the book is about how you can really think about human senses, human beliefs, human behavior as a very Bayesian phenomenon with prior probabilities we update from the world. Now, what that implies is that predictions, when people hold false beliefs, or what you might call conspiratorial beliefs, they should, in theory, get updated with new information. So if you believe that the USA never went to the moon, for instance, the moon landings were hoaxed, you should be able to update that information. When as new information, loads of photos come back from the moon, and loads of people tell you who you trust that these, the news, they'll tell you, no, we did go to the moon. Look, here's this photo of the flag flying on the moon. Here's the photo of. Now, if it were just the 2 options, or the 2 hypotheses of either we didn't go to the moon or we did, then this new information should update you towards it. But because of the way, because there are multiple hypotheses, and because someone has a very strong prior that these that they didn't, and then when you can explain this in evidence of photos coming from the moon, you can explain it in one of two ways. You can explain it either they're real photos from the moon, or people are trying to lie to us and trick us, and they've set up a studio backlot in Hollywood, and it's actually who was it? Stanley Kubrick.
Yes.
There we go. Yeah.
I just went to do a quick Google search. No.
I was quick enough. I was pleased. But yeah, so what that means is when you get these two competing hypotheses, when new evidence comes in that is compatible with not compatible with your original hypothesis, your original idea that we didn't go to the moon, and that's the end of it. You can either move your confidence towards actually we did go to the moon, or it can go increase your confidence in the hypothesis people are lying to me. And that's how when people have got very strong priors in something, very strong beliefs in something, the same evidence that would convince you or me to believe we did actually go to the moon will convince them that the mainstream media is lying to them, and that so I find this really interesting because it allows you to say this is how people end up with conspiratorial beliefs or different beliefs from the same evidence, without saying these people are strange and weird and somehow wrong and bad. You can just say, well, they had different beliefs to start with, and from that different starting belief, they're updating rationally with the new evidence. And I think it's a more, I don't know. Otherwise, you're forced to say people who believe the Earth is flat, or that.
I was just going to say that.
Yeah, that's the classic, isn't it?
Flat? Is it flat? And did we go to the moon?
Yeah. Or vaccines cause autism or whatever.
Yes.
The more or the Pizzagate stuff that the United States is run by a cabal out of a pizza restaurant in Washington. That's these things, which to be clear, I'm not convinced about myself. I don't think they're necessarily completely true. Anyway, so
big one. Here's the big one for the U.S. We have the election coming up with it, right?
Yeah.
Better candidate.
Yeah, well, oh God, if I'm going to get, yeah. But yeah, I do have opinions.
For this episode.
Yeah, but you see what I mean? But that's exactly it. You can see when a politician gives a speech, there's lots of sort of people talking about how there was a classic bit of research showing that people will have different opinions about a speech when they learn that it is by Hillary Clinton or Barack Obama or Donald Trump or George Bush, whatever. Yeah. And people say, well, that's people got annoyed about that, and they said, well, this just shows that people are irrational, and they base their policy opinions on who says things rather than on the policies themselves. But actually, it's perfectly rational. I trust some politicians less than other politicians because of my priors, and that's a purely Bayesian thing, right? I have my prior beliefs about stuff, and so it makes if Einstein were to come and tell me that that space-time is that time is relative to space and all this sort of stuff, I'm okay. You I trust you. You know what you're talking about. But if sort of like John P. Nobody off the street comes and tells me that, I would be a bit more sort of I don't know what you're talking about. That, but obviously we do know that Einstein was right. But that you can there isn't such a thing as trusting people and having priors in their trustworthiness, and that makes perfect sense.
Like, the biggest thing that all I have to say is that you can't trust somebody who has been a convicted felon. Anybody that knows that anything about the U.S. politics, a ham sandwich is better than both candidates.
Oh, it's going to be a tough year, isn't it?
It's
going to be a tough year.
And on top of that, have you heard of someone named Vernon Supreme?
I don't think so, no. Oh, lovely. Yeah, it makes sense.
He wears a boot upside down on his head.
We have guys like that here, yeah.
Okay, it gets better. Half of his stuff, you'll get a good giggle out of this one. Half of his stuff makes more sense in the current political state of the U.S.
Yeah.
And he believes that there should be a miniature pony that is an emotional support animal for every household.
There's There are guys like that in the UK. There's the Monster Raving Loony Party puts up candidates at most elections, and there's a guy called Count Binface who turns up wearing a garbage can over his head. Yeah.
Yep.
And actually there was sometimes it's quite funny. He comes up with quite good, he did. I think he got more than the Conservative Party candidate one election.
Yep.
I can't remember the details of it.
I think the best one here that is currently running as an independent, it's an independent politician. They legally changed their name to literally anybody else.
That's good. I like that. That's funny.
So it was a good.
Yeah, that gets a laugh. I like that. That's nice.
When seeing that, so every single prediction, we do need a laugh, and
yes,
especially as mathematicians. I'm going to bring it back to something that you do have in the book. I'll call it a little Easter egg. Mathematics conferences always get interesting.
Yes. Yes, they do.
So what is going on with the University of Minnesota?
Okay, so So I don't know why it's on the servers at the University of Minnesota, but there were these amazing there were these amazing conferences.
Yes.
So firstly, right, Bayesian statistics, as we've established, are the only way of saying this is how likely my hypothesis is to be true, given the evidence. But most scientific statistics never, because in the early 20th century, scientific statistics moved away from that. They went towards what we now call frequentist statistics, which is the exact opposite. The how likely am I to see this result, given a hypothesis, which is people, has pros and cons, but a lot of people a lot of people didn't like it and were sort of quietly using Bayesian stuff in the background. And in the 70s, it started to come out a bit more into the open, and people they started having these conferences, particularly in and around Valencia, which honestly sounded pretty crazy. They were the first sort of real Bayesian world meetings, and at first they were just in the daytime because it's very hot. They'd do their work in the morning. They'd have a siesta. They'd do some more work, sort of 6 till 10 in the evening, and then they would have big parties where they all sing. It was great. I won't try and sing it because I'm not a natural singing voice sort of person, but there was a excuse me. But there was a song called Thomas Bayes' Army from the Battle Hymn of the Republic. Mine eyes have seen the glory of the Reverend Thomas Bayes. He's stamping out frequentists and their incoherent ways and all sorts of stuff. It goes on for ages. And there were these drinking, they had Bayesians in the night to this tune of Strangers in the Night, and they had like a Bayesian, like a virgin. There was the full Monte Carlo, which had a bunch of middle-aged statistics professors taking off their clothes on stage in front of a screaming crowd. It sounds like a lot of fun, honestly.
That actually sounds like a normal math conference.
Really? Oh, that's lovely. Oh, that's good.
So it's not too far from the truth. At least some of the dinner parties.
That's good.
I don't know about some of the clothes being taken off.
No, that might be more than we need. But yeah, the fact that you tell me other maths conferences also do it. There was one guy said that he had a sweatshirt saying Bayesians have more fun, but maybe that's not true. Maybe all mathematicians have loads of fun. I don't know.
All I can hear is someone singing "Glory, Glory, Probability."
Yeah. I was tempted to break into song. I just thought it's probably not. It's not best. It's not for the best. But yeah, it does sound like it was a load of fun. They also apparently one of the Bayesian statisticians who was there says that they all took a boat out and went for a swim off the coast, and then the winds got up, the boat blew away when they were stuck in the water, and he says there was a decent chance that like half of the top Bayesian statistics professors in the world would have all drowned in one moment. They were rescued. It was fine, but that would have set back the Bayesian statistics quite badly if that had happened.
I think out of all of the songs that so far that I've heard is that there's no theorem like Bayes' theorem. There's no theorem we know.
Yeah. It's great, isn't it?
What?
Yeah, I mean these are all they're I mean, they're nerds letting their hair down, aren't they? It's great. I absolutely love it. That was at the sort of when Bayesianism was starting to come back into vogue, and because I think a lot of people had independently rediscovered it over the decades before, but Ronald Fisher and people had sort of tried to stamp out Bayesianism in the 1920s pretty much, but people like Alan Turing independently rediscovered it because you need it. You cannot work out how likely something is without Bayes. So, and people want to know how likely stuff is, when you're doing code breaking or when you're doing, people are using it for artillery, working out artillery or mechanics. Lots of Silicon Valley. It was reinvented several times in Silicon Valley by people just like, yeah. And so you just need it. You need it. So,
you need it from like stock market predictions to weather forecasting and even self-driving cars.
Yeah, absolutely. And anything that is making a prediction,
yes,
making predictions under uncertainty, you need Bayes, and that whether that's the human brain or a self-driving car or Google Maps or code breakers, anything like that, you cannot do it. Artificial intelligence in general, you just cannot do it without Bayes. And so the in the mid to late 20th century, it came back in, and people realized that it's important. I mean, it is still not standard in science. Still, most scientific research is done using frequentist models. So that is things like p-values. When we declare something statistically significant, that's a frequentist model. That is saying, I will be this result that we found will be unlikely to happen by chance. So under the hypothesis that there is no result here, that there is no effect here, I would only see it one time in 20 or something, which is the opposite of how likely is my hypothesis to be true given this result. But nonetheless, it is. The Bayesian systems are getting more common. There are ways, I was speaking to a pharmaceutical a statistician who worked in pharma industry for a long time, who's saying again, you need this to be able to say, I think this drug is 75% likely to work, whatever. You cannot make statements like that without using Bayes. And I think it's great that it's coming back more into mainstream, and obviously it explains 1,000 other things as well.
Yes. Now, out of curiosity, what is something that you want people to know about the book that you want to drive home to an audience, to anyone who's listening about this?
Sure. Okay. Well, I mean, probably the idea, the thing. I tell you what. My sort of takeaway from sort of a life, using it in my own life, sort of thing, has been that when we talk about the intelligence is about prediction. Everything that humans do, that everything that AI does, everything is about predicting, and that's Bayesian priors and so on. But what's really crucial? Well, so the two things that fall out of that, right, are firstly, you don't have to say I think this thing is going to happen or I think this thing is true. You can say I'm 80% sure that this thing happens, and then you can update or up and down with more information. And it means you don't have to sort of doggedly defend some position. I definitely think politician X is good or whatever. You say I have a strong probability that this person is going to do good things if they get into office, and then when I get new information, oh God, they're not as good as I thought. I can bring it down a bit rather than just saying, and now I abandon that belief. I don't have to sort of have yes or no answers to everything. I can have probability estimates on stuff. Also, I think it's really, we spend an awful lot of time arguing, especially on the internet, because everyone argues on the internet, and God knows I do as well. Is this thing, yes, exactly. Is this thing, is this, I don't know, is it woke? Is it racist? Is it eugenics? Is this thing, does cancel culture exist? All these names and things that we put on stuff, right?
Of course it does.
Well, but, but when we have these arguments, quite often people don't actually disagree about any of the facts. That's, with the cancel culture example, no one's sort of really arguing that that people haven't lost their jobs because of things they've said. They're just trying to say there's an argument over whether we should call that phenomenon cancel culture. And the thing about what Bayes tells you is beliefs are predictions. If I call it cancel culture, if I don't, does it change any predictions I make about the world? If it doesn't,
no.
Maybe I don't think so. I don't think it does. But so maybe we can just say, it doesn't matter what we call it. I predict that if you said these certain things on a podcast, then you would probably be at risk of losing your job, which is why I'm so careful about things I say on podcasts. And that, whether you can choose to call that cancel culture or not, but the point is, beliefs should be predictions about the world. Beliefs that you hold should imply some prediction that then can be falsified or not. It can come true or not, and therefore can adjust your those probabilities down the line. If they don't have any, if there's no sort of prediction attached to a belief, then kind of what's the point in it? Call it cancel culture, call it not, whatever. That doesn't matter. We're just arguing about a word rather than about any sort of facts about the world. And I think that is the biggest takeaway for me, is that that beliefs should have probabilities and predictions attached, and if they don't, they're kind of meaningless.
Wonderful.
Cool.
And anything else that you would like to add?
I mean, only that you should all go and buy my book, obviously. I think that's probably the crucial thing.
I thought it was very entertaining.
That's brilliant. I mean, that's what I go for. It is not always easy to write books about maths that are funny. I've tried to do it. I think sometimes I've succeeded. And I think that's
it was actually quite brilliant. I was reading through it, and I'm like, I try to do a book. When I sit down, I do a book in a day.
Oh, wow. That's very impressive.
So usually, if I can enjoy it in an afternoon, a couple hundred pages in an afternoon, you have done well.
Brilliant. Well, I'm honestly, I'm thrilled to hear that. I'm absolutely thrilled. That's really lovely.
Yes. So, and in that case, I thank you for coming on the show.
It's been a pleasure. It really has.
It's been an absolute pleasure.
Cool. Well, thank you, Autumn. And if I could just reiterate my point about everyone should definitely buy the book, that would be great. Yeah.